A, B, C, D, suppose. So this is the piece of paper that you should be starting off with. Let me know if you have found one. Because we'll be using this piece of paper, it will be an important tool for our investigation today. Also get hold of a pen or a pencil with which we'll be able to write on the piece of paper. Got it? Okay. Okay, I see Tanvi, Sagar, and Arya says yes, they have got one. So this will be vital to the next part of our discussion. Okay, so the first step, we want to fold a paper to get a square out of the rectangle. How do you think we can do that? How can we fold the paper to get a square out of this rectangle? We have this rectangular sheet of paper. There should be a way to folding it in a way that we get a square out of this rectangle. Think a little bit about it. We want to convert this piece of paper. We want to fold it in a way so that we can definitely mark out a square in this rectangle. Four folds? No, actually you will need just two folds, one vertical and one horizontal. No, that will not help. Think a little bit more. Think a little bit more. Okay, Swastik says half it. If you want to half it, you have to match up the edge A with D and B with C. So you'll get a. You really don't need to make it. Okay. Triangle fold. What is the meaning of that? Can you be a little bit more precise? B to C and C to D. I wonder how that would help. Take a little bit of time. Actually try folding the paper. Actually try folding the paper and see how can you get. So if you have joined late, if you have joined right now, then this is the tool that you will need to attend today's discussion effectively. So you start with a ABCD, a rectangular sheet of paper. So as a first step, we want to get out a square out of this rectangle. So since this is a more of a seminar style class, I cannot give you much time to actually think about it. But the idea is this: pick A, pick A and place it on BC. So like this. So there will be a diagonal fold. And your A will be somewhere here. Do you see what I'm saying? All of you? I'm folding around the diagonal. I'm folding in a way that A falls on BC. Let's call it A prime. And I am making sure that this line that we have here is the crease of the diagonal. So if we fold along this, fold so that this crease is prominent. Do you understand what I'm saying? If you get this, now your paper should look somewhat like this. Like this. So this is the folded portion, and your paper should look somewhat like this. The point A is here, B stays here, this is C, this is D. Suppose this point is X, and this point where it hits BC is Y. Okay, so we can forget about this portion. You can tear this off, right? Tear this off, and you have something called a square sheet of paper with you. So you have A, B, X, Y. You have A, B, X, Y. All right. So mark the point A as 0 and B as 1. In fact, you can do better. You can mark it as a coordinate. So we have a framework to work with. So suppose we mark this as X as 0, 0, Y as 1, 0, A as 0, 1, B as 1, 1. Got it? Do you have this? Do you have this markings on the square sheet of paper that you get? Okay. Now, just by folding the paper, find half comma 0 on the segment XY. How would you do that? Just by folding the paper, how can you find out half comma 0 on XY? Place AX, exactly. That's very simple, isn't it? So you now have a crease along the middle. You now have a crease along the middle. Send A to B and X to Y. And you have this point M, which clearly is half comma 0. Okay. Okay, now comes the real challenge. Can you find out 1/3 comma 0 by folding alone? Find 1/3 comma 0. Give it a try. By folding alone. Find 1/3 comma 0. Do not rush. This will take a little bit of time. Shurabh, how do you know what is a third? How to fold any three equal parts? That's the key idea, right? You're not allowed to approximate. You cannot approximately fold in 1/3 of the part. Approximations are not allowed. Yes, you could probably glue three papers. But what we are more interested in, Swastik, is to fold this particular paper in a way so that it works. Okay, I'll give you a little bit more time. The problem is this, that you can only fold by saying that, okay, that point goes to that point. Remember, what is a folding? I told you A goes to B, X goes to Y, something like this, right? Or maybe to a particular side. You have to say some things like that, something precise, what you mean by your folding. Okay, maybe I'll give you a little hint. First, find out the diagonal. So, step one, find the diagonal. How do you do it? How would you find the diagonal? Well, you send A to Y. you send A to Y. Okay. So what kind of a crease will you get? You'll get something like this, isn't it? Now, what should you do? How should you fold to get 1/3, 0? So if you have 2 points on this sphere, on this square, you can always fold it in a way so that that crease or the line passes through those 2 points. That's possible. So when I say how to fold, I'm asking you what type of line do you want to draw? Okay, I'll again probably tell you. Excellent, excellent rhythm. Indeed, fold along AM. Fold along AM, all right. So you have this intersection point of the creases. Okay. So let's call this point N. Now what? Remember, you can always, this is step 2, fold to find AM. So when we are folding along squares, we basically get a right angle for free, right? This right angle or that right angle. So any fold that is along that right angle, parallel to that right angle, is basically also a right angle. AM is A is this vertex, swastik, and M is this one. A is the top left vertex of the square, and M is the midpoint that we have found. All right, now fold. Okay, that we can do, or it is same as saying that fold AX across N, which in this case will be a little bit more appropriate. Fold AX across N, so that you can get a crease like this. My claim is that this point S is 1/3, 0. Can you prove it? Can you prove that that point S is 1 by 3 comma 0? So let me put the square here one more time. Let's quickly draw what we have already drawn. We have A, B, X, Y. This is 0, 0. This is 1, 0. This is 0, 1. This is 1, 1. We fold it in the middle to get the point M and the midline. We then fold it along the diagonal BX. Like this. And then fold along AM to find out this point N. So basically you intersect the lines BX and AM and then fold AX along across N. Let's call this R. Or maybe I named it S, I'm sorry. Let's call it S. Name doesn't matter. So can you show that this point is 1/3 comma 0? This was half comma 0. Can you give me the what is the equation of the line Bx? Can you tell me that? Okay, I think Vedam has a good solution. Equation to Bx is definitely x equals to y, right? And what is the equation of Am? What is the equation of the line Am? So if you are familiar with a little bit of coordinate geometry, then you will immediately see that it is y equals to mx plus b. So b is the y-intercept. In this case, the y-intercept is this. So y-intercept is the point at which the line hits the y-axis. So that's 1. So y equals to mx plus 1. Now we need the slope. The slope is 1 minus 0. So that's the difference of y values divided by the difference of x values. So that's negative 2. So the equation of the line is y equals to negative 2x plus 1. So you have two equations, y equals to negative 2x plus 1, and we have this one, which is y is equal to x. So we want to solve these two equations. So let's plug in y equal to x. So x equals to negative 2x plus 1, which is 3x equals to 1, which is x equals to 1/3. So you see that's the x coordinate of n, 1/3. And since y is equal to x, therefore n is also 1/3. Y coordinate is also 1/3. So if I drop a perpendicular from n on x-axis, then obviously it will be 1/3, 0. Okay, so this is a little bit of coordinate geometry. You can also do the same thing, I believe, that from normal geometry, as Rhythm points out. It's a ratio of sides, so yes, you can do that. Now let's continue this algorithm to find out. So this is 1/3. If you join these, so let's mark this point as well. Okay, now let's use a different tactics. Let's join AS. Join AS. Let's call this point T, the intersection point of BX and the midline, MF. So let's join. So now join AS like you joined here, and also join ST. So you got 2 points again from the 2 points of intersection. What are the coordinates of these 2 points? These 2 green points. Quickly compute the coordinate of these 2 green points. Let's call this one N1 and this one T1. What are the coordinates of N1 and T1? Or more importantly, if I drop perpendiculars from N1 and T1, then I'll get S1 and N1, suppose. So Rhythm points out that N1 is 1/4, 1/4. And the strategy is same, isn't it? The strategy is that this is, you find out the, so we already know the equation of the line Bx is y equal to x. Find out the equation of AT1. Equation of AT1. What is the equation of AT1? Or I'm sorry, AT, not AT. Actually, I'm making a little error in the symbols. This is S. So AS rather. So what is the equation of AS? Equation of AS is y equal to minus 3x plus 1. Just like we got this one, right? Yes, Tanvi, that's correct. So where is it intersecting with the x, y equal to x line? So you replace y by x. So yes, solving, you are solving now y equal to x and y equal to negative 3x plus 1. So now replace y by x. So x equal to negative 3x plus 1. So 4x equal to 1 or x equal to 1/4. So that is the x coordinate. Now let me just quickly redraw the picture and see what's going on here. So we have this 0, 0, 1, 0, 0, 1, 1, 1. We fold it along the middle, or rather we can also do this by joining the two diagonals. We get this point, which is half comma half. Drop a perpendicular from here, so you can actually fold it along this line. You get the point half, or rather half comma 0. Then you join these two and drop a perpendicular from this intersection point. You get 1/3. Then you join this one and drop a perpendicular from here. You get 1/4. What did you get for this one? Did any of you got that? The one that I just drew, the coordinate of the green point. So we already have the equation of the line AM. AM was y equals to negative 2x plus 1. So we know the line AM's equation. Pritam says 7 by 18. Let's see if that's right. What is the equation of this line? Let's call this RS. What is the equation of RS? Well, we can use y minus half equals to m times x minus half, where m is the slope. Now what is the slope? So this point is 1/3 comma 0, so slope is half minus 0 divided by half minus 1/3. So half divided by 1/6. So this is 3. So y minus half equals to 3 times x minus half. So you get y minus half equal to 3x minus 3/2. So y equal to 3x minus 1. So the equation y equal to 3x minus 1 and y equal to this. So let's equate them. Negative 2x plus 1 equal to 3x minus 1. So 2 equals to 5x. X is 2 by 5. Simple enough. So this x coordinate of this point is 2 by 5. What is the y coordinate? So y is equal to negative 2 times 2 by 5 plus 1. So negative 4 by 5 plus 1. So that is 1 by 5. So this is 2 by 5 comma 1 by 5. So the coordinate of, so this point is 2 by 5 comma 0, the green point. Do you follow? So this is a, now there is a interesting pattern that is at play here. Recognize the pattern, I guess. That you start with a square. Let's call it 0. This is 1. I'm omitting the y coordinate because it's just 0 here. If you draw these two lines, you have, and drop a perpendicular from the point of intersection, you have half. Let's write it as 0 by 1 and 1 by 1. Okay, now let's join these two. Drop a perpendicular again. We got this as 1/3. But look into the curious way of finding 1/3 from these two. 0 by 1, let's call this special sum. 1 by 2 is equal to 0 plus 1. Suppose we define it like this. So you just add the two numerators and you add the two denominators. So you have 1 by 3, which is precisely the next point that we have got. Okay, what is 0 by 1 special sum 1/3? What is 0 by 1 special sum 1/3? That is 0 plus 1 by 1 plus 3, right? So if you join these 2 points and drop a perpendicular, you will get 1/4. Okay, and if you join these two and from here drop a perpendicular, so what is the special sum of 1 by 3 and 1 by 2? What is the special sum of? So that is 2 by 5, isn't it? And that's what we found. Do you realize? We found the point 2 by 5 by our hardcore computation. So what my claim is that every time you join this one, so can you guess what this will be? What this point will be? It will be 1/5, exactly. Okay, can you guess what this point will be? So you join 1/4 with this and then drop a perpendicular. It will be 2 by 7, indeed. So A by B special sum C by D equal to A plus C plus B divided by B plus D. This is a special type of a sum. It's often called the Faraday sum. Anyway, we found a geometric construction that actually realizes the Faraday sum. And you can actually reflect this picture. It is applicable in this particular geometric construction showed up. And more importantly, it has, well, if you want to know the deeper connection, then it's actually leading to something called hyperbolic geometry, which is extremely intriguing in many sense. So there is strong evidence to suggest that that the universe is hyperbolic. But anyway, that's not a big deal. Let's not go there today. So we have this beautiful picture in front of us. Now, as the last step, do this. Squash down all the triangles, all the verticals into a single point. So pull down the verticals in a way. So what kind of picture will we get if we do that? We start with these two semicircles. And then we'll get a bunch of other small semicircles as the verticals are all pulled down to one point. So in effect, we will get a picture like this. We have two verticals. Let's keep them as it is, as they are. We have now a semicircle like this. Then we have two semicircles like this. We have two like this. And it goes on. Okay? Do you see how it is going on? You can, in fact, draw this without lifting your pen. You can start with one semicircle like this, then half it, and then go like this, and then go like that. And you can keep on doing this. They are all the squashed down versions of the triangle that you see here. So you have basically squashed down all the verticals. You have basically squashed down all the verticals to the x-axis, pinned them down. To imagine a little bit, I guess. But if you imagine, you get this particular picture, which is this one. So anyway, this beautiful construction in many ways leads to, it's called a Faraday diagram. Well, it's just a part of the Faraday diagram. It's one of the initial tools that led to the world of hyperbolic geometry. So in the hyperbolic space, which I have not defined, of course, Each of these semicircles will be considered as a line. They are examples of straight lines. And one can do certain computations with these straight lines, and just like our Euclidean space has different type of geometric problems, the hyperbolic space has different type of geometric problems. And sometimes they match. Sometimes one is useful for the other. For example, you may have heard about inversive geometry. It uses a tool called inversion to solve problems in geometry. Inversion is nothing but example of a reflection in hyperbolic space.